All right, well, welcome everyone. I am JJ. Let's go ahead and tackle an example problem. So this time around, we're saying we have this 500-pound weight here is hung from our system of cables and a spring. We know that it's supported by spring AC and cable ADEF, and then spring AB. We're going to try to figure out what's the tension in cable AC, what's the force in our spring, and how far did the spring stretch when all of this was hung. This should just be a particle equilibrium problem. So if we're tackling one of these, we want to look at what's the point here where everything passes through. Everything's going through point A. So we start setting up our free body diagram. We want to circle around A. Everything that passes through that circle is going to be a force in our free body diagram. Everything else we're basically just cutting away and saying it doesn't matter. For example, our cable ADEF, it doesn't matter that it goes down and then straight down. We're only going to look at this 5, 18, 17, or 15, 18, 17 triangle. Our free body diagram, let's sketch it down below. If we draw this in, we have our particle A. I know that straight to the left from here, I cut cable AC. So going straight to the left, we have a tension in AC, T, AC. I know that going down and to the right, I pass through spring AB. So we'll show one force there, down and to the right, a T, A, B. That's a spring, but we still just show it as one force because forces show up in our free body diagrams, not springs. And we're given that this is a 50-degree angle from vertical. So go ahead and come in and label that as well, 50 degrees from vertical. The very last thing we have is our ADEF cable. I'm going to show that just straight up and to the right as it leaves point A, because that's the particle we're drawing the free body diagram of. So this is my TADEF, but I know that if it's 500 pounds here at the weight, then it's 500 pounds as it goes up to our pulley at E. It's the same cable. So our tension is never going to change along that. Same cable, same tension, no matter how it changes angles in there. Which means as we get all the way back into our particle, this is still a known 500 pounds. Let's move that a tiny bit so it doesn't hit my picture. Up here, this is 500 pounds. And we know our dimensions for that. It's a 15, 8, 17 triangle. So we can label that 15 horizontal, 8 is the diagonal or the vertical, 17 is our hypotenuse in there. I have two unknowns, TAC and TAB. I can find those. Again, remember, I'm just treating this as a force. I'm not trying to sub in like F equals KS, my spring equations, into my free body diagram. It just overcomplicates everything. Let's just roll with our unknown forces. Once I have those, I'll figure out F equals KS. So if I'm starting this out, I have two unknowns in the X direction, TAC and TAB, but only one unknown in the Y direction, only TAB. So let's sum forces in the Y first. If I do sum of the forces in the Y direction, I'm going to have, well, my 500 has a component that goes up, my vertical, my Y, 8, or my hypotenuse, 17, times the force, 500. My TAB goes downwards, so I'm going to subtract this out, minus TAB. And because my angle comes from vertical here, I want to use the cosine to get my Y component. Cosine of 50. And finally, I'm setting up an equilibrium equation. Every time I do this, I actually get what am I doing here, but I always have to say this all adds up to 0 for equilibrium. Get that equals 0 in there. But TAB is my only unknown. I can solve for this, and I'll get that the tension in cable AB is 366.05 pounds. And that's my first answer in there. With that known, I could go in and do F equals KS or some of the forces in the X to get one of my other two answers. Let's go ahead and do my other equilibrium equation. If I sum up forces in the X direction, well, now that I know 500 and TAB is really 366.05, I can solve for TAC. So let's go ahead and apply equilibrium there. This is equal to 500's X component, so the X leg of our triangle, 15 divided by the hypotenuse, 17, times our force, 500, plus the x component of TAB plus TAB, because my angle comes from vertical. To get that x component, it's opposite 50. I use sine. Sine 50 minus TAC. Because it points to the left, we subtract it out, and that gets us to 0. TAC is my only unknown in here. I can solve for TAC. TAC is equal to 721.59 pounds, which is my second answer for everything. All that we still need to find is how far did this spring stretch before it settled into this situation given in our given picture. And we can do that just saying, I know that my force equals Ks. Or in this problem, TAB, the force in the spring, equals Ks. Which is going to get us that TAB we found above is 366.05. Equals our K value. We were given that's 130. 130 pounds per inch. That's not the force in the spring. That's our K value, the spring constant for this. How far it stretches per force that's put on it. 130 times our final variable we're looking for, how far it stretched, S. Just 366.05 over 130 gets us that the spring stretched 2.82 inches, which is going to be our final answer for our problem. Again, particle equilibrium just comes down to some forces in the x and the y. If there's a spring, use F equals Ks. But hopefully this was a useful video for you. If it was, hit those like and subscribe buttons. Stick around, watch more videos. Let's get you in A with JJ.